In this video, we're going to work more example problems where we're given a function and we want to represent that function as a power series. This is part 2 of these types of problems. For the problems in this video, we're going to focus on, so we're using this base function here as a reference point, and the idea is to put our function into a form that sort of mirrors the base function. This is just a power series with the c sub n equal to 1, and it's centered at 0. So it's a geometric series with common ratio x and first term equal to 1. And for where it converges, this is just, we know this is equal to the first term over 1 minus the common ratio. For the problems in the previous video, we just algebraically rearranged our formula to put it into a form like this, and then went from there. But in this video, we're going to be either differentiating or integrating the function along with this power series to get the forms similar. So for these problems, we're going to need to be able to know how to differentiate or integrate a power series. All right, so if we look at this function, what we notice is that f prime of x is equal to, so what's the derivative of this? You have 1 over 5 minus x times the derivative of 5 minus x, so minus 1 over 5 minus x. And we notice that this form here is similar to this form. So the idea is, what we're going to do is we're going to go ahead and represent this function, this derivative here, this function, as a power series, just like we did in the previous video. And then we're going to integrate that power series to get back here. Okay, so how do we represent this as a power series? Well, it's just like we did in the last video. Well, what we do is, let's bring this minus sign out front. And then we need to, so we've got the numerator is 1, just like this. But then we need to make this term here a 1. So we're going to factor out a 5 here, and we have 1 minus x over 5. Okay, so you've got okay, so if, you know, any power series like this, as far as where it converges, you can think of as a function. And so we can see, if we compare this to this, this is just g of x over 5, positive x over 5, right? So f prime of x then is we just replace this with x over 5. And there we go. So that's f prime of x. And so we know that this is equal to, okay, and the idea is, if we integrate both sides, we're going to get, we know that the integral of this here is, well, let me put dx. We know that this is going to be equal to natural log of 5 minus x plus c. Well, let's leave off the plus c for the moment. So it's going to equal this, right? So we need to integrate, to solve this, we need to integrate this to get another power series. Okay, now, so, all right. We'll bring in the plus c when we do the integration of the power series. The only thing you want to keep in mind, because you can end up missing this, we talked about when we went through the textbook, that differentiating and integrating power series is really simple. But be careful that you, so yeah, all we're going to do is to integrate, we're just going to go to the x term and do the x to the n plus 1 over n plus 1. It's that simple. However, like here, we have x over 5. So it's like, think about if we were differentiating this with respect to x, this wouldn't be n times x over 5 to the n minus 1, because then you have to use the chain rule. So you want to rearrange your series to get the x by itself. But if you can't get the x by itself, then you can think about, okay, you would do the chain rule here. If you were differentiating this, all we would do is come to this term and say n times x over 5 to the n minus 1 times the derivative of x over 5 is just 1/5. And then we would update it would change this to n is equal to 1. So you could still integrate or differentiate with this x term not being just alone as x. But you just have to be careful. You have to, if it's not alone, you have to consider that you might have to do a substitution, like an integration substitution, or use the chain rule. But also note that, like, if it's not centered at 0, if you just have like x minus 3 to the n power, well, then there is no chain rule or substitution that's needed in that case, right? If you have like the x minus 1 to the n, this derivative is just n times x minus 1 to the n minus 1. And same thing with the integral. You don't have to do a substitution. Okay, so let's do this. Okay, this is, let's separate these two. So you've got x to the n. Okay, so now we can go ahead and do the integration. So that's this integral, and the plus c is going to come in over here. So we've got c minus 1/5, and we just leave this as n is equal to 0. We don't have to change the starting point. And then it's just x to the n plus 1 over 5n times n plus 1. And then what we could do is say, so c minus, let's bring in that 1/5, 5 to the n plus 1 times n plus 1. Okay, but now to simplify this, what we can do is, so natural log of 5 minus x is equal to, we can say, so c minus, let's change this to the starting point to n is equal to 1. So that becomes 5 to the n, so it's n times 5 to the n. And then, right, because here at n is equal to 0, each of these is 1. So now that we change it to n is equal to 1, just those become, we want those to be, the first term to be 1. Okay, but now we want to get this constant though. We're not done. So what we do is we set x equal to the center of the power series. That's 0. So when x is equal to 0, you have natural log of 5 is equal to c. And what is this? Well, for some power series, the first term results in a constant that has no x in it. But this isn't the case. Every single term has an x in it. So this is going to be 0. So c is equal to natural log of 5. So there we go. We've solved for c. That means this is equal to natural log of 5 minus okay. So now we just need to get the interval of convergence. So the interval of convergence, it's all about the series portion, right? This converges everywhere. It's just for what x's can we plug in and actually get a number. So this is not geometric, so we need to use the ratio test. So x to the n plus 1 is x to the n times x. 5 to the n plus 1 is 5 to the n times 5. And then Okay. Oh, well, this is all absolute value. So, okay, now the n portion is never negative, going from like n is equal to 1 to infinity. So, okay. Now, what do we do from here? This is the absolute value of a sub n plus 1 over a sub n. Well, okay, yeah, we need to take the limit as n goes to infinity of this, and that needs to be less than 1 for it to be convergent. I think for the problems in the previous video, I forgot to, it simplified to where there was no n's, there's no n term at all. And so I just said we need to set this less than 1. Well, yeah, because as n goes to infinity, if there's no n terms, then there's really no limit. But I meant to mention that we were kind of in the background, there is a limit involved. If all the n terms cancel out, well, then the limit as n goes to infinity is just the x term, right? Well, we need to think about here, what is the limit as n goes to infinity of this? That needs to be less than 1. Okay, well, as n goes to infinity, we can see that this is going to go to 1/5. So we've got that 1/5 times the absolute value of x. That needs to be less than 1. So multiply both sides by 5. The absolute value of x needs to be less than 5. So x, if you solve this absolute value inequality using the, we know how to solve these from algebra. This is the solution. Now, actually looking at the question for these problems in the textbook, it doesn't tell us we have to find the interval of convergence. We don't need to check the endpoints. It just wants us to give the radius of convergence. So the radius is going to be 5, we can see, centered about 0. But we could have potentially, we know that there's a rule, if you differentiate or integrate a power series, the radius of convergence doesn't change. The interval of convergence might change in the sense that the convergence of the endpoints might be different, but the radius doesn't change. So we could have potentially, it might have been easier just to note what the radius of convergence of f prime was, and then I could have just reported that after. So let's keep that in mind for the next problems. Okay, so let's bring in the comparison. So, well, remember that we can kind of take this x squared, we can separate it. And then just if we find the power series representation of this, then we can just bring in the x squared after. So what is the derivative of arctangent of x cubed? Oh, I'm in degree mode. Didn't mean to do that. Okay. So we should be able to work with this. We're going to think about a separate function, h of x, that's equal to the arctangent of x cubed, and therefore h prime of x is equal to 3x squared over x to the 6 plus 1. Okay, so can we represent this as a power series? Yeah, if we could do this, take this 3x squared out front, and then we've got what? 1 plus x to the 6th. What is this? This is this is 1 minus x to the 6th. You see? So if this is g of x, then that means that this is g of minus x to the sixth. But why are we doing this? Because if we can represent this as a power series, then we can integrate this. When we integrate it, what do we get? This. But I know we still have this x squared, but we'll get to that. Okay, so h prime of x is equal to 3x squared, and then so minus x to the sixth to the n. Okay, but now we can just go ahead and just bring this 3x squared into the summation. It's not a function of n. So we've got, so minus 1 to the n, and then 3 times x squared times x to the 6n. Okay, so this is, we've got minus 1 to the n, and then 3x to the 6n plus 2. Yeah, there we go. So that's h prime of x. That's this. Okay, so what we're gonna do is we're gonna integrate this. This is both sides of the equation. Okay, now we want to check that is the x term. Is there like any do we have to do a substitution or something, or like simplify this some more? No, the x term's by itself. It's just x to a constant. So we've got, so what is this integral? Well, that's this. Let me get rid of, okay, so now we just need to take this integral. Well, it's just x to the 6n plus 2 plus 1, then over that same number. What's 6n plus 2? It's like all of this plus 1. It's just 6n plus 3. So it's, we don't have to change, oh, well, we're going to have a c. We don't have to change the start point or anything like with differentiation. So it's, we're going to have minus 1 over n, and then 6n plus 3. We'll have a 3 here, and then x to the 6n plus 3. Now, if you notice, we can simplify this because we can write this as, so this is 3 times 3n plus 1 so this is okay, so now we want to get c. So we want to say, what is, let's set x is equal to 0. Arctangent of 0 is 0. And if we look here, so when n is equal to 0, do we have just a constant term with no x? No, there's always an x in every term. So all of this goes to 0 when x is equal to 0. So c is equal to 0. Therefore, arctangent of x cubed okay, now we're not done though. This is arctangent of x cubed. We've got this x squared. So we've got this. So we want to bring this x squared into the summation. So x squared times x to the 6n plus 3 is going to be x to the 6n plus 5. Okay, and actually this should be, when you factor out a 3 here, this becomes 2n plus 1. The 3's cancel, and this is 2n plus 1, right? Okay, now potentially you would think that maybe we could change this to n is equal to 1 or something and simplify this, but with these factors multiplying the n, I think that this is the simplest we can get. So, because like these don't increase 1 by 1 by 1, right? When n is equal to 1, when n is equal to 1, this is 3. When n is equal to 2, this is 5. You know, when n is equal to 1, this is, when n is equal to 0, this is 5. When n is equal to 1, this is 11. So, but still, there we go. So this is equal to, we'll put it like this. There we go. Now, the radius of convergence, so we integrated what series? We integrated this series. We turned this, we integrated this series. And so the radius of convergence of both of the series that we obtained after the integration and the series before the integration are going to be the same, but I don't know how much that helps us. It's not that big of a deal. We're just going to have to do the ratio test on either one of those. So which one would be easier? Okay, yeah. Here's H prime. So yeah, it looks like this would be easier to do the ratio test on than this, right? Again, these two, well, wait a minute. No, because yeah, these are going to have the same radius of convergence. But then once we multiplied the x squared, we've kind of changed everything. So let's just go ahead and do the ratio test on this. So the absolute value of, okay, so n plus 6 times n plus 1 plus 5. So 6, that's 6n plus 6 plus 5. That's 6n plus 11. So x to the 6n times x to the 11th over, we got the absolute value, okay, 2 times n plus 1 plus 1, that's 2n plus 2 plus 1, that's 2n plus 3. So that's 2 to the 2n times 2 cubed. All right. Now, 2 to the 2n plus 1, that's 2 into the 2 to the 2n times 2 to the first, and then x to the 6n times x to the fifth. All right, so we got, and then, so let's see, 2 squared is 4. Yeah. So, and yeah, in the previous video, what I was doing was I was just getting to this point and saying this needs to be less than 1, which is true. But I meant to mention that the real idea is it's the limit as n goes to infinity of this. But since there's no n, then this is the limit as n goes to infinity. Right? It's the ratio test. So, okay. Well, x to the 6 is always positive, so we can just remove the absolute value. So x to the 6 over 4 is less than 1. Multiply both sides by 4. Okay. So a polynomial inequality, we do this. And let me just go ahead. I don't want this video to get too long. So, all right. Solve x to the 6th minus 4. And so, I mean, I'll show you. Okay, what we would do is I could just type in the inequality, but. And so, like, these are the boundaries. Like, you know, this is how you solve polynomial inequalities. I mean, let me just These would be so it's going to be between 2 to the 1/3 or minus 2 to the 1/3 and 2 to the 1/3. I can, it's less than, yeah, minus 2 to the 1/3 to 2 to the 1/3. So that's the radius of convergence. It's not asking us to find the interval of convergence, probably because these problems would take too long, but there you go. From 2 to the 1/3 to 2 to the 1/3. So the radius then is 2 to the 1/3. Okay, so if we look at this, what we can think about is, what is the derivative of this? The derivative of this, if this is g of x, g prime of x is going to be that. So derivative of the top times the bottom, that's 0, minus the derivative of the bottom is minus 1. So yeah, let's write that out. Or it might be 1 over 1 minus x squared. Let's see. Derivative of the top times the bottom minus derivative of the bottom is minus 1 times the top all over. So yeah, it's actually positive 1. Okay. So there's the derivative. Okay, and so what is this equal to? How do we differentiate a power series? Well, we change the first term to 1 because the first term, well, it depends. You have to make sure that if the power series has a first term that's not a function of the variable, then you change the first term to 1. That's not a hard rule for like any power series. It depends on the series. But for here, in this situation we do, and then we just do, so x is by itself. There's no like chain rule or anything. X and that's it. And the radius of convergence is going to be the exact same. We'd have to check the interval, but we're not doing the interval of convergence here. But the radius of convergence would be the same. It's going to be 1, centered about 0. So what we have here is a new kind of a new something we can compare with, and that matches this form, right? We can't really pattern match these two like we were doing before, but these we can, right? So what we can do is we can say we want to, these are actually already pretty matched up. So this is x times 1 minus 4x You see? So this here is g prime of minus 4x. These match up. So therefore f of x is equal to x times and then we just plug that in here. So this is n times minus 4x. And there we go. So now we just need to simplify. And, well, okay, before I erase that. So we know our radius of convergence because we've gone from, let's see, well, so, okay, these two radiuses of convergence are the same. The radius of convergence of this is the same as this, but then we're multiplying this x, so to me that means that changes things. We're going to have to just check the radius of convergence. If we didn't have this x here, and we just started with 1 over 1 plus 4x squared, then we know the radius of convergence because it's the same as the derivative. But once we bring in this x, that changes things. So we just have to, it's not a big deal, it's just more work. Okay, so we've got, let's see, we want to bring that x inside of the summation. So, okay, minus 1 to the n minus 1, then n then 4 to the n minus 1, then x to the n minus 1. Okay. What do we have? Minus 1. So x to the, this is going to be x to the n. That's nice. So this is just n 4 to the n minus 1, x to the n. Well, we could do this. N x to the n over 4, right? This is 4 to the n times 4 to the minus 1. So wait, no, this is, forgot the 4 to the n. Okay, so there is that's this as a power series. Now, we just need to determine the radius of convergence. So since we multiplied this x, we're going to go ahead and, we don't know, we have to check. So we're going to go, it's not a big deal. We're just going to need to do the ratio test. So, okay. We've got, so the absolute value okay, so n plus 1, and then 4 to the n plus 1, and then x to the n plus 1. Okay, and then we've got n. Okay. So all right. Now this term here is always positive and just goes from 1 to infinity. So okay, so there's the absolute value of a sub n plus 1 over a sub n, but remember for the ratio test, we're taking this limit as n goes to infinity. That's what I forgot to mention in the previous video. This as n goes to infinity, this goes to 4. So this is the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. And for the series to converge, this needs to be less than 1. So this, dividing both sides by 4. Okay, so this is solving this absolute value inequality. So there you go. The radius of convergence is 1/4.